In the last video, we defined an inner product for Cn, and it's the standard inner product. We'd like to take this and figure out complex inner products in general now. So let's review what we figured out about Cn. So the standard inner product on Cn, we defined it to be just you take all the entries over here and you multiply x1 bar times y1 plus x2 bar times y2, xn bar times yn. It's like the regular dot product in Rn, except that you conjugate all of the entries of x. You leave the entries of y alone, you conjugate the entries of x. Okay, that was nice, and it had some nice properties. So the first property that we want to look at is that it's not linear in the first factor. It's almost linear. See, if you take the sum of two vectors in the first factor, you can split it up. You get the first one plus the second one. But if you multiply the first vector by a constant, remember you're conjugating all the entries of C. So you don't multiply the result by a constant, you multiply by the conjugate of that constant. This property of being linear under addition, but you have to conjugate under scalar multiplication, it's called being conjugate linear, or sometimes it's called being antilinear. So anyway, whenever you have a constant buried in the first term, when you pull it out, you pick up a C bar, not a C. However, it is linear in the second factor. You have a C in front of here. You're not conjugating the things on the second factor, so that just pulls out as just a regular constant. So it's linear in the second factor, conjugate linear in the first. Now, symmetry is a little weird. If you switch the order of y and x, it changes the answer. And the reason it changes the answer is that over here, you're conjugating all the y terms before you multiply them by x. And over here, you're conjugating all the x terms before you multiply them by y. But if you then conjugate the whole thing, you unconjugate the x terms and you conjugate the y terms, and you get what you would have had over here. So the symmetry, order does matter, but it only matters up to taking conjugates. The size of this is the same as the size of x dot y. Size of y dot x is the size of x dot y. They're just complex conjugates of one another. And finally, positivity. For any non-zero vector, the inner product of x with itself is real. See, inner product of x with y or y with x, that's a complex number. But x with x is actually a real number, and not just any real number. It's a positive real number. And we take its square root to get the length of x. So that's how things work for Cn. These are the four basic properties of complex inner products. And if I give you any rule that satisfies these four axioms, conjugate linear, linear, symmetric, and positive, then we will call that an inner product on a complex vector space. So let's look at some examples. The first example, of course, is the standard inner product, because that's the thing we're trying to generalize. Okay. By the way, a couple useful ways to write the standard inner product. You can write it as a product of a row with a column, where the row you get by taking the transpose of x and conjugating it. In other words, x transpose conjugate times y. Remember, vectors are columns. Then we have an L2 inner product. If, say, we're talking about the space of all polynomial functions of a variable t, then you can take the inner product of f with g to be f of t bar times g of t, multiply them together, and integrate from 0 to 1. Or if you have some complex matrices, you could take the inner product of those two matrices to be the trace of A transpose conjugate times B. So the transpose conjugate should be a recurring theme. Here we had x transpose conjugate times y to do for Cn. You get the same thing for matrices. We'll see a lot more about transpose conjugate in future lectures. And then here are some less standard examples. There's nothing to say that we can't vary the formula, and instead of taking x1 bar y1 plus x2 bar y2, we'll just take x1 bar y1 plus twice x2 bar y2. It's still a sensible inner product. It still satisfies the axioms. Or we could take an L2 inner product where we multiply everything through by e to the minus t squared before we integrate. Also a perfectly good example. Now, a really important thing for a real inner product space was that it satisfied the Schwarz inequality. Schwarz inequality said that the inner product absolute value was less than or equal to the size of the first times the size of the second. Well, the same thing goes for complex inner products. Only now these bars don't mean absolute value, they mean the length of the complex number. So the length of the complex number x dot y is bounded by the length of the vector x times the length of the vector y. And they're equal if x and y are linearly dependent, and they're unequal if x and y are linearly independent. And to prove it, we modify the proof of the real inequality. Now, I'm not going to provide all the details. I'm going to give you a sketch, and I'm going to ask you to do the proof on your own, because working through the proof, given the proof I already gave you for the real inequality, seeing how to tweak things is a really good way to get a feel for complex inner products. So here's one approach. One approach is to say, use positivity and say 0 is less than or equal to x plus ty dotted into x plus ty. Only now when you expand this out, you're going to get some terms that don't have t's in them, terms that have t's, and terms that have t bars, because it's conjugate linear in the first factor, it's linear in the second factor. So it's still going to be true for all complex numbers t, and if you pick the right complex number t and do a little bit of algebra, the Schwarz inequality will pop out. Another approach is to multiply one of the vectors, like say y, by a unit complex number. This is a number whose length is 1. So e to the I theta times y has the same length as y. And when you do that, you can get this inner product to be real. And then you can follow the reasoning of the regular Schwarz inequality without worrying about complex t's, because t will turn out to be real. Okay? So either of these approaches will succeed in proving the complex Schwarz inequality, and I'm going to leave the details to you.